Welcome back to INST 314, Statistics for Information Science with Shawn Janzen. We're starting a new topic module this time on ChiSquare, specifically looking at the goodness of fit. ChiSquare is the first of our inferential statistical tests we are going to be exploring over this term, and I'm excited to get started with you on this first topic, 5.1, Foundations for the ChiSquare Goodness of Fit. In this particular lecture, we're going to be talking about not only the ChiSquare test as a whole, but we're also going to be introducing the concept of degrees of freedom. Future videos for the ChiSquare Goodness of Fit, we're going to show you how it actually is done by hand, and I'm going to have follow-up walkthrough videos on using Excel and R. So let's go ahead and introduce the ChiSquare. ChiSquare, now it's pronounced Chi, but if you want to call it Chi, I'm okay with that too. I'm not going to worry about it. So the ChiSquare is a test that we use with categorical variables. These are the nominals and the ordinals, with only a few categories. Technically, you can use it with ordinals that have many categories. You can also technically use it with numerical variables. However, you will start to see once we do this by hand that we're going to be using bivariate tables. And if you have an ordinal with many categories or a numerical variable, it's going to make your tables very large, meaning you're going to have a lot of things to compute and your tables might degenerate. We'll look more at that later when we get into some of these analyses. But for now, just keep in mind that we're looking at these for nominal and ordinal variables for these small chi-squares. I guess I should put an asterisk on that. Those of you going into data science may be using chi-squares to compare entire data sets, massive tables, to see how they compare with each other. But that takes it down a different vein, and you guys will explore that when you actually get to your data science stuff. So generally, let's go back to the chi-square here, talking about that, and it comes in two flavors, the goodness of fit and the test for independence. The goodness of fit has only one variable, where the test for independence has two variables. Both of them take the same sort of job, where we are comparing observed frequencies to expected frequencies. What are the values we actually have, and what are the values we're expecting to find, given the values that we have. Now, we're going to talk a little bit here about the chi-square distribution. This is the chi-square curve, right? Some of the characteristics about this is that it is non-negative. That means on the xy axis there, it's bound at 0. It cannot have negative values. It's not symmetrical, meaning the shape of the curve is generally unimodal, but it has a long tail that'll run out to one side. And the shape of the curve is going to vary a little bit depending on the degrees of freedom. The degrees of freedom are calculated for a chi-square goodness of fit as n-1, and its variance are 2 times the degrees of freedom. As many possible distributions in terms of the shape, but as the degrees of freedom increase in number, you find that the shape of the chi-square starts to look like a normal distribution. Don't be fooled, it is not a normal distribution, and we'll be talking more about the normal distribution in the next sections, but it starts to look like it. And, of course, we're going to be needing chi-square critical value tables to help us find the probabilities for these things. Now, wait a minute, let's take a time out here. I just mentioned a few times this concept called degrees of freedom. What is a degree of freedom? This is the first time we're talking about this in the class. A degree of freedom is a numerical value that kind of gives us this idea of how many things do we need to estimate in the values that we have. So let's take, for instance, the table that I have up on the screen. We have values 6, 8, 5, 9, 6, 8, 4, 11, 7, x. And I want to know what's the value of x. Well, if I tell you that the sum of all of the values here in this vector is 69, you know that there are 10 values, and that the mean of those values would be 6.9. So if we just did some basic algebra here, 64 are the value totals that we have, plus x equals our sum of 69, and so then x has to equal 5. Now, since x must equal 5, it cannot vary. But we have 9 other data points in this vector that can vary. So we have 9 degrees of freedom. And I leave a link here to a Statistics by Jim blog. I highly recommend the Statistics by Jim blog. He's got some fantastic posts there. But this one in particular goes a little bit more into the degrees of freedom for statistics. Now, if that analogy seemed a little off for you, let's try a non-stats type of example for degrees of freedom. Let's say you like to have hats. You've got a nice collection of hats, and in this case, you have one for every day of the week. And each day, you're going to choose one hat to wear, and the only rule is you can't choose a hat that you already wore. And so we're going to go through the days of the week. On the first day, you have 7 hats you can choose from. On the second day, you've already worn 1, so you only have 6 left to choose from. And by day 6, going and going, you only have 2 days left. And then by day 7, you only have 1 hat that remains. So from the 6 out of the 7 days, you got to have choices. But by the last day, you had 1 value that had to be that one specific thing. So in this case, our degrees of freedom are 6, since 6 of the 7 days could vary. Keep in mind, degrees of freedom are the number of values that are allowed to vary in a given, in this case, vector of data. I just said a few moments ago that the chi-square distribution, the shape of that distribution, is going to be based on its degrees of freedom. And so on the screen here, we have a screenshot from the Manga Guide of Statistics, and we see on these 4 different displays different shapes of all the same. They're all chi-square distributions, but they have different shapes because they have different degrees of freedom. When there's only 1 degree of freedom, the chi-square distribution looks rather concave, and it hugs very closely towards the origin of this graph. As chi-square distribution has a degree of freedom equal to, that line that's hugging the y-axis is starting to come down, the tail's starting to bulge out a little bit more towards the right. By the time we have chi-square degrees of freedom equal to 4, we have this unimodal bump that's starting to emerge, and the left side of the distribution is hugging down at 0, and the rest of the curve is starting to bow out a little bit towards the right. When degrees of freedom equal 8, the curve is starting to move towards a more central part of the graph. It's starting to look more normal. Remember, it is not a normal distribution, but it could start to look like that. The blue shaded areas under there are the critical value areas, and we're going to come back to those really soon. But on this next graph, I really want to start to illustrate a little bit more about that distribution and how it relates to any given chi-square critical value. When you obtain a chi-square critical value, we can use the chi-square distribution to help us figure out what is the probability of obtaining that particular value. Every value has a chance of what you can find it if we assume a null hypothesis is true. Remember, that's tying it back to the p-values and alphas when we're saying if you want to see what the chances of finding something, this is the chance of finding that particular value when a null distribution is true. The same idea of the graphic is going to come into play when we talk about the critical values and if our chi-squares are statistically significant or not. Look for the bonus video I'm making that's going to specifically talk about critical values and how they tie back to alpha and p-value and determining statistical significance. So let's go ahead and keep moving into the chi-square goodness of fit foundations now that we've talked a little bit about the distributions and the degrees of freedom. So when we're talking about a goodness of fit, we said before that it's only one variable. And part of this is because what we're testing it against is our prior knowledge and expectation about that one variable. So the chi-square test for the goodness of fit is going to test the significance for the distribution of a single variable, only one. And we're making claims about a population's proportions on that one variable. So the chi-square the chi-square in general is what we call a non-parametric test. And by non-parametric, I mean we're not going to require assumptions about its variance or its normality. Variance is something that only numerical values have, meaning you can take a mean, standard deviation, and variance. But when we're dealing with categorical variables, it's not appropriate to worry about taking means, standard deviations, variances, because they are not numerical. Therefore, it falls into what we call a family of tests called non-parametric, which rely on things like frequency distributions across tables, median values, things of this nature. And we'll see non-parametric tests here and there through the term. Now, non-parametric tests are easier to calculate than their numerical counterparts, their parametric counterparts. However, they're weaker than their parametric counterparts, only insofar as that you have a greater chance of committing a type 2 error. And that gets a little bit into more the math side of things that we're not going to explore too much in this course. But just keep in mind that non-parametrics aren't necessarily as strong, or powerful rather, than their parametric counterparts. So going back to the goodness of fit with hypotheses, remember this is an inference test, the first one that we're working on. So all of these are going to have a hypothesis that goes with it. And the one specifically for the goodness of fit says that we're going to compare the observed frequencies we have to the population's frequencies, or the proportions we have to the population's proportions. And so the null hypothesis, keep in mind a refresher, that null hypotheses are always meaning that there's no difference, no effect. And so in this case, with the goodness of fit, The null hypothesis is that the data meets the expected distribution. All right? We can also say that there's no difference between the distribution that we have and the one we would expect to find. Conversely, the alternative to this is that the data does not meet the expected distribution. It does not match with that which we'd be expecting to find, regardless if it's frequencies or proportions. So if we want to say this a little bit differently, we could say with the null that the population's distribution is correct. Ours is not significantly different from the population's, and it is the correct distribution. Alternatively, we could also say that the population distribution is not correct. Now, that isn't to say that the population distribution is wrong. We're just trying to say that our knowledge of the population distribution is perhaps out of date and needs to be updated. And so in this case, it was incorrect, and we have new knowledge now that can help update our population distribution information. Now, when we put this into the statistical significance testing for the goodness of fit, we have to set ourselves an alpha. Remember, alpha is how much risk are we willing to take, the total amount, our ceiling. Back to the speed limit analogy, the alpha is our speed limit. We have also the degrees of freedom. The degrees of freedom for goodness of fit test is k minus 1, where k is the number of categories you have in your particular variable. Using the chi-square's degrees of freedom and the alpha values, we can find a chi-square critical value. And so that chi-square critical value is going to be a number, and we will reject the null hypothesis when the value in the chi-square that we obtained, the statistical test value we find through our calculations, is larger than the critical value. We will be statistically significant. Conversely, we could say that if our p-value of that chi-square test that we obtained is smaller than our alpha, we can be statistically significant as well. And what this is really saying is that the chi-square the chi-square test value that we've obtained has a probability. And that probability is so low of getting that specific value that it can't be due to chance alone. That there's some underlying difference that makes the distribution we've calculated different than the one we would be expected to find. And therefore, we are statistically significant and we can reject the null hypothesis. So keep in mind, the chi-square critical value we test and obtain has to be larger than the critical value, or the p-value of that chi-square obtained value has to be smaller than our alpha. Again, the bonus video is going to help clarify this a little bit more. So with our chi-square test here, we're going to have two assumptions for it. First of all, we're going to assume independence. All of the different observations in our distributions here has to be independent of each other. That means one value is not going to be influencing another value to take on a specific characteristic. And then also we want to have a decent sample size. And by decent sample size, each cell in our table has to have a count of at least 5. If we don't, the math can start to get a little weird and possibly break down your chi-square value. You're still going to get a number, but that number might not be right. And also keep in mind, when that number of 5, that's sort of a soft rule. If you're dealing with test values that are in massive amounts, then that 5 might be a little bit higher than actually 5 relative to your large samples. And we'll see this more when we start doing this in R and how it works out. So in that point, I'm going to leave this video with you now, and in our next one, we're actually going to pick up doing a chi-square test by hand and watching the results.